Здравствуйте.
Хорошо.
Добрый день, слышно?
Да,
Да.
Да, это хорошо.
а меня как слышно?
Ну, так приемлемо.
Ну, так приемлемо, да.
Нет, ну,
Хорошо.
конечно, высококачественный микрофон, по-моему, не повредил. Но, тем не менее.
Высококачественный микрофон в другом месте, к сожалению.
Нет, ну это...
У нас выходной тут,
А что случилось?
день непорочного зачатия, понимаешь.
Нет,
Поэтому на работу я не пошел. Вот.
непорочное зачатие Богоматери, надо полагать.
Ну, видимо, да. Как это называется?
Нет,
Да.
ну, в принципе, могло бы быть и Христа, но тогда бы как-то плохо согласовано с Рождеством. Как-то несоответствие какое-то. А так, может, и все.
Ну, а он что, 9 месяцев, что ли?
Нет, про это, по-моему, доктрина ничего не утверждает.
Может, он быстро, так сказать,
Нет, ну,
на
по-моему,
2 недели.
по-моему, на эту тему доктрина ничего не утверждает. Нет, но католическая церковь признает также непорочное зачатие самой Богоматери.
Окей.
И
Сейчас я
поэтому это,
посмотрю,
это
как это
может происходить
называется.
в другой день.
Периадос.
Как они установили этот день, я не знаю, но это самое. В принципе, это ничего не
Таких
противоречит.
тонкостей я не знаю. Это называется Инмакулада Концепсион. Сейчас я посмотрю, что это значит.
If you work in a Catholic university, you should know things like this.
But I don't work in Catholic University. I just, well, I give classes there.
Yeah, 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 yeah. But how they choose the day? It was installed in 1854. But
1850,
how how they decided the day?
the day.
Why
Well,
it's
it's
today, not any other day?
8th of December, yes. So,
Yeah, but it was the day when the announcement was made, not not when the date when the conception was made.
yeah. Well, not in Orthodox Church, I don't know. I haven't even heard
No,
that.
Orthodox Church disagree with this.
Disagreeing
With the
with
idea of that the Virgin Mary did not have any sin.
so they don't agree with it.
Yeah, they don't agree. So they need something to disagree. So they disagree on this.
Okay. Let me try to share something where I will probably write something. So, and I can probably even share some link where potentially you can also write,
Okay, great.
unless this is some kind of but this is Microsoft, so I just chat.
Okay, let me see. How can I? Whoops.
So, can anybody enter this link?
No, first I need to copy it. It's not that easy. How? Why I cannot copy it?
At least I can write,
Okay,
supposedly.
open in browser. What? It doesn't want to be opened. Wait a bit. Copy link. Okay.
Okay, well, I don't know. Shall I start or Have anybody succeeded to
Yeah,
read?
let me check. I succeeded to see this. However, I see only letter C, while on your
Ah,
screen I see much more. Let me
Vereshchagin?
try.
Yeah, Vereshchagin collapses. Yeah, somebody writes something.
Now I wrote some. Yeah, that's me. But there is a huge delay. As you see, yeah, I finished. Yeah.
It's typical for Microsoft.
Big delays are typical from Microsoft.
For this thing, I forget how it is named, but I have tried it, and it's very, very slow.
Yeah.
I don't know. On my side, it's not slow. I mean, it's okay. I mean, so maybe okay. So for collaboration, maybe it's slow.
I mean, rather large files. Say my notes for a lecture during COVID, something like this.
Ah, okay. Well, let's see. Maybe if I go along with it, it will become slower.
Okay.
But I don't know. So I can try to start. I don't know. With, let's
Yeah,
try.
probably.
So I wanted to tell a bit about some classical, well, some simple things. So one classical things, I guess you can name something like gold and undoing. So, and they call this topic inductive inference uh, from positive data. So let me try to explain. And then, so what we have, we start with a family F. It's just as well, it's just a set of infinite languages, let's say, I don't know, over 0, 1 alphabet, for example.
So what is infinite language? It's just
It's just that there are infinitely many strings in that language.
yeah. Okay.
So let's assume for simplicity that they are infinite. So I don't know, it could be just the set of all languages. It can be the set, I don't know, for example, the set of all regular languages or the
And
family of
each
all.
of them is decidable, or we have no idea. Not.
No, 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 no. So far, no,
Yeah.
not necessarily.
And
Just
there are no description. There is no description of a language. Just a language as a set.
well, I mean, let's say we will be working mostly with the case when f is countable, and then you can say, well, then you can order them, and then somehow there is a description, which is just a index of the language in that ordering.
Yeah.
I mean, and then we will also work with the case when, I don't know, for example, I don't know, one example could be the language of all, the set of all context-free languages, for example. Then the description is clear. I mean, for example, the corresponding context-free grammar or something like that.
Yeah.
But so far, it's just forget about computability for a moment. Then just the arbitrary set of infinite languages.
Yeah.
And then we want to define what means that f is identifiable in the limit. Identifiable in the limit. Well, what does it mean? Let me try to say it. What happens? So adversary, there is an adversary. So adversary secretly selects a language from the family. And then starts enumerating strings of L. In some order that the adversary also might is able adversary can select an order, but the only promise is that eventually every string from L will be given. right? And then basically what we need to guess is we need to guess what language the adversary enumerates from. What happens is that, okay, what we see is actually we just see in any moment of this enumeration, we just see some finite sequence of strings. And after any of these finite sequences, we can indicate some language from the family, language L head from the family.
But indicate in which sense? That's why I was asking.
Formally it's just a function from finite sequences of strings to F.
So it's not an algorithm, we just somehow...
This is so far not an algorithm.
Yeah, okay.
It's just a game theoretical concept.
This is not an algorithmic problem. It just
you can then ask, what about an algorithmic version of it? But let's first discuss. Just forget computability issues.
Yeah.
And in the limit, the guess should be correct, right?
In the limit, so for any, yes. So starting from some moment, the guess should be L.
Mm-hmm.
So
For any
language,
language that adversary selects, and for any enumeration, for any ordering of enumeration of strings of L, that starting from some moment, we should give L. Only L. But like the moment from which we are given L can depend on L itself and on the enumeration in principle. This is what is called F is identifiable. And then if it's possible, then F is called identifiable in the limit.
For example, if F is finite,
if F is finite, then it's identifiable in the limit.
Yeah, because we can just single out a string from a finite number of strings that distinguishes all languages and wait.
Let's be more accurate. How exactly we are doing it? So what's the algorithm? We have a finite family. So let me write a statement. I don't know, proposition. F is finite, then F is identifiable in the limit. So
for any two languages, we fix some string that is in one language and is not in the other language. And then we wait. When we obtain a tuple of strings which distinguish our language from all the others, we are sure that this is our language and we output the correct answer.
I see, but there is a problem that there can be a language and then there be like a super language. I mean, like a language that contains it. So
so the idea is, of course, we should select between languages which contains all the strings.
Yeah, but and among them we should select what?
Somehow the minimal in terms of which strings are there, or most simple one, I don't know.
Yes, so the algorithm, let's try to say, so we have, so what's the algorithm? So assume we have some finite sequence of words. Let's phi prime be a subfamily of, then let's only consider like consistent languages. So what's the algorithm? Remove all inconsistent languages.
Mm-hmm.
Yeah.
Okay, so what will happen if we do so? This means that if the enumeration is large enough, what we will also we will be only left with the language itself and maybe its supersets.
Maybe we should output the smallest consistent
The smallest language, indeed. You should output when you see, well, okay, if you see a situation when you only have one when all the consistent languages, there is a minimum, like all which is in all the other, just output this language. And this will be correct from some point, because for any enumeration of any language, there are just finitely many languages that are not supersets. That means that our language has some words that are not in that languages. So all these languages will be gone from some moment. So from some point, there will be only our language, our true language from which we are enumerating, and some supersets, some super languages that contain it. But okay, we see that all of them are consistent. Let's output the smallest one.
No, I don't understand. Imagine among our family, we have all finite languages. Then all the time we can assume that this is a finite language.
No, but wait, we have finitely many languages. Languages itself are infinite. Well, I mean, maybe you can consider this with finite languages, but let's, for simplicity.
Okay, let's assume that languages contains all I don't know, all zero string and something else. And if we have some non-zero strings, and then
Sasha, what is the family?
So first of all, we agree that all strings of zeros are in our languages.
No, Sasha, the F is finite. The family is finite.
Family is finite. Oh, sorry.
No, family is finite.
Family is finite. Sorry. I somehow missed this. Yeah.
I'm sorry. I forget the rules of the game. We should give an answer at some predicted moment, or
No. At each moment we give some candidate, and our goal is that starting from some moment, our candidate is correct in the limit. That's why I say
we have no idea.
So we produce a sequence of infinite sequence of languages, and we required to produce a sequence which is constant on the language after some moment.
Yeah. So at every moment after we have seen some strings, we produce one language, but then we get a sequence because we get newer and newer strings. And this sequence should stabilize.
I see.
Yeah. Okay, but for example, another example is to show. Can anybody show why, for example, the family of all regular languages is not identifiable in the limit? Family of
all infinite regular.
All infinite regular languages, let's say. Yes. Regular languages is not identifiable in the limit. By the way, there is, okay, well, let me give another thing, that if the family is identifiable in the limit, then it's most countable. Let me make this proposition. F is identifiable in the limit, then F is finitely countable. Why is that?
How do we enumerate? Oh, sorry, the language is itself countable. Sorry.
I don't know. There's phi is the set of languages. So languages are subsets of 0, 1 stuff. So in principle, they could be uncountably many, right? So
yeah.
Sasha, I think that each language in the family can be identified. So fix some enumeration for every language.
yes.
And then fix a time when our guess is correct. And the prefix, the sequence of strings available at that time, plus that moment identifies the language, because we can apply our algorithm to that sequence and just obtain our language.
It's true. So it's just our, yes.
Not just we have finitely many possible beginnings of the game, and so if only and in each of them we have some output, so we have only countably many outputs.
Yes, and every language from the family should appear as an output.
Yeah,
Okay.
and every language from the family should.
Well, okay. So then, okay, is it clear? And then the example, for example, why all the family of all infinite regular ranges is not identifiable in the limit.
No, let's think about.
So what I would start off, I will start.
No, but maybe someone already knows this.
Yeah, well, yeah. So who
Bruno,
knows?
you probably already got this. Why the regular language is not identifiable?
No, I'm still thinking.
Probably we need to fix some simple subfamily of this, which is already not identifiable. For example,
yes.
I would guess that the language of the form a to the n b star, it's always regular. A to the n b star, right?
Which can, you mean?
Okay, a n b star. So you just check language L sub n, which is this.
Yeah, it's ln.
Okay, no, just this. N is the following regular expression, right? So all the words that start with A and A's, and then there's just B's.
Yeah.
That's my guess. Maybe it's
okay. So, but I agree that this is a regular language. What then?
And then you want to say that this family is not identifiable in the limit. But I would say that it is, right? Because just I receive any word and then I already know what's the language, no? Because by the number of A's in the beginning.
I just wait until we get first B, and then I know exactly what is the language.
Yeah, so what?
We don't even, we get the whole word, right? So I mean, just, we don't get like A, and then B. We get the whole word. I mean, we get, for example, is the first example with L3, then we start enumerate, I don't know, we have a word A, B. This is the first word that we get.
And we already know what is it.
And we already know that's L3.
That's a stupid
So
example.
what about languages with finite complement? Can we, maybe that
Languages
helps.
with finite complement are regular.
Yeah,
right.
Surely.
And probably you're right. So let's try to, but how would you, so languages with finite complement, cofinite languages.
Yeah.
Why they are not identifiable in the limit?
Well, I just took an example where previous algorithm fails because we don't have a smallest language.
True.
Yeah, but let's prove now. That it is not identifiable. So imagine we have some algorithm.
And just feed that algorithm with all the sequence of all the strings in lexicographical order, for example. Then at some time, it should put a correct guess. Right?
Yeah.
So
I mean,
should be
the time depends on our language.
So the language is just all strings, yeah?
Yeah, assume that the language is all strings and just feed all of them in some order. At some time, the algorithm should say that this is the set of
0,
all
1
strings.
star.
But then we decide that we won't output some certain string at all. And
but then the algorithm can change its opinion. Why?
It doesn't know that the string won't appear.
Yeah, but still it can change the opinion. I don't understand the argument.
Yeah, the argument should be improved. Indeed.
So I would say let's try to actually enumerate all start enumerating all words except some word X. So in some moment, the algorithm should say this is all strings without X.
Mm-hmm.
Yeah.
Then let's give X and I don't know, all the strings of length 100. I mean, all the strings that we might have missed. I mean, that's up to some length. Then again, let's take some string Y that we haven't seen yet and start enumerating everything except this Y.
Okay, and our algorithm will change its mind infinitely many times. Then.
Yeah, but in that way we will actually enumerate all the strings. So it will be some enumeration of all the strings. So actually the algorithm should have told us that, I don't know, it's some...
And so this a real language is still regular somehow.
I mean, the
Right.
real language will be just the string, the language of all the words. We will enumerate all the words. What we are doing, we are waiting for an output which is different from the 0, 1 start. So what we are doing, we just take any word that haven't been enumerated yet. We start enumerating everything except this word. And by definition, at some moment, the algorithm should have output a language that consists of all the words without this word, the one word. And then we switch again.
But
So
if the algorithm indeed outputs the set of all words, what do we do?
No, but it couldn't, because if we enumerate everything without this Y, at some point we should indicate, by definition, this will be enumeration of all the words without Y. So then at some moment the algorithm should say, starting from some moment, the algorithm should
But
say...
in the middle it can say that these are all words.
Yeah, in the middle it can say, but what we are just... In step number n, our pooling
Yeah.
argument works in steps. In step number
Yeah.
n, we want to ensure that we will once more, we will enforce the algorithm to output something which is not the set of all.
Yes, and if it decides to stay, to keep saying it's the language of all strings, well,
then
we
it will
didn't
be
say
incorrect
why.
because we did not
That-
add some string, and still
Yeah,
we are
in
okay.
case we choose this language minus y, then it is incorrect.
Yes. Okay, so we have seen some examples. So basically, as I understand, like something in 67, Gold have defined this setting, and probably he have shown that, for example, this thing is not identifiable in the limit. And then in 1980, Dana Angluin gave a characterization when the family is identifiable in the limit. So let me state this
Positively.
Yes.
Yeah.
So theorem of Angluin. And there is also a computable version, but let's try to state it first without.
So I had some impression that this is all general computability theory, and so it should not be that people should know it for a long time. But indeed, from 1980, it's a long
some
time.
people know it for a long time. Others people are not aware of it for a long time.
And they discover it all the time. Okay.
Yeah, I would say I would actually will later speak that I will try to tell something that could be actually considered long ago.
But it's your new nice theorem.
New nice theorem, but okay, let's start with Angluin, with the classic theorem. So, a countable family. Well, we know that the family should be at most countable. If it's finite, then identify. So a countable family is
identifiable in the limit.
Identifiable in the limit. If and only if for every language from the family there exists a finite subset of this language such that L is a inclusion minimal language in the subfamily F sub S, which is just the set of all languages from F that contain S.
And minimal is наименьший or минимальный, so we require that
It
smaller
means
than
that
everything.
there is no proper subset,
No proper subset.
but there could be other minimal, and minimum is the different thing. Minimal is a weaker notion. It means that there is nothing.
It's not
No proper subset.
And so L is not necessarily an only minimal language. There will be several minimal languages.
Yes. Just no proper. I mean, I guess if I say it like that, it's a little bit minimal. Not minimal, not unique, maybe. Minimal, maybe not unique. Maybe not unique. Or I can say that there is no other language which is a proper, no proper subset of L contains S. Or equivalently, no proper subset from the family, no proper subset of L from the family contains S. Okay.
Yeah.
Is the statement more or less clear?
Yeah. Now maybe someone, for example, Kolya or Bruno or Georgi or whatever, or Danya, can explain at least in one. I guess one direction should be simple.
I guess from right to left, this direction should be
If there is for every
more or less
L.
Sasha, more or less we have already the L. So we wait until we get this S.
No, so what is the algorithm? We have some already have some strings.
We wait until we form some S finite part for which our language is one of the minimal languages.
But we don't know what's the language, so can you be more? I mean, we should be more precise in the sense that we just see.
Wait. Assume that we
can think that we have a let's see, we have a sequence of languages L1, L2, Ln, and so on, and we have these subsets S1, S for each of them.
Yeah, but fix this SN, so right?
I mean, I don't
but currently we have only some strings W1, Wm.
And we wait until for some n, we get all the strings from Sn.
They contain. We want that one of Si is already there.
Take and some n such that
Sn is among Wm.
And just
while such as n doesn't exist, we don't worry because we are sure that whatever our enemy does, it needs to provide some.
Until that time we can output any, for example, L1. But when it happens, we switch to Ln, I guess, and that's it.
Take some n such that Sn is like that, output Ln.
All right. So, and if this is incorrect, that at same time we will, then our language is another minimal language in that family, which just contains some string which is in that language but not in our language.
Say it again. So Then that at some point
So
we can
wait.
change.
So algorithm is fixed. Okay, so the algorithm is just we have a sequence of words and we take the sum n such that S of n is contained in this the word sequences that we have, and then we output ln.
So we take
we have to
any
prove
n.
that in the limit the algorithm is correct, right?
Yeah. So let's assume that actually we are
But I don't, Kolly, I don't understand. Wait a bit. I don't understand what Kolly is saying. So we took some n.
Right.
And then we never change it or what?
No, we change, we wait.
But when we change it?
I say that we change when we get a string that is outside ln.
We assume that we know ln?
No, wait. But probably, so first of all, I guess you want to also assume that you should only take n if only ln contains all these things.
Right, sure.
So
Right.
then, so Sasha, what's the algorithm that are suggested? The algorithm, actually, what formally? We take a sequence of words and we output some ln. Which ln? We take some n such that this thing holds, such that all the words that we see are in ln, but Sn is already contained there, and we output this ln.
So we look for any ln which has this property.
Yeah, well, for which n should we clarify it, or?
No, I don't know. If Kolly agrees for every n with this property, that's...
I agree for every n, sure.
But then can you prove why it's identifiable in the limit then?
Okay. Assume that, so take the first moment when we output ln.
But
Then-
can I just start an argument just saying that assume that the real language from we enumerating is L sub k, some language L sub k.
Yeah.
And we want to show that from starting from some moment, we will exactly, essentially we want to show that there is the k will be the only language with that property.
So first of all, if the language is LK, then at some moment we will have enumerated all the elements of SK.
Right.
So can LK will be one of the candidate for the output.
Yeah.
And the problem is what is not shown, that maybe there are other candidates for the output.
It may, of course.
Yeah. So I would simplify.
Why would it stabilize then?
Yeah.
No, I try to explain why.
Yeah, say it again. Just.
Assume that LK is not correct.
But no, I mean.
What? No, LK is the real language. It's ground truth.
So there should be some
So
other
our output can be incorrect.
You are right. I try to explain from the other end.
So you try to explain why, if we always output LK starting from some moment, then that's a real language.
No, I want to show that if the real language is LK, that's starting from some moment, we will output LK. That's my argument.
In other words, you want to show that any other language will eventually. Well, I mean, if it's not enough, but we need to show that any language which is different from k, from starting from some moment, will not satisfy one of these properties.
No, we can agree, for example, that we take the minimal k, minimal n.
Then we take the minimal k, and then we will just be. It's a good remark, because then we will just have to care about finitely many other languages that we need to eliminate. I mean, in the sense that all they have to be gone.
Since LK will be a good candidate starting from some moment, we don't need any languages with big index.
So the algorithm is actually take the minimal.
You are right. We need to take minimal, right? Minimal, right? Without that, it is incorrect. I guess.
Probably, but I mean, in that case with the minimal, it's easier. So now we just have to show that any other language from some moment will not satisfy these properties if we enumerate L sub k. So why is that? And we have to use somehow this property that no proper
So
subset.
LK is a correct language. At some moment, we will
And then
find...
we have some other language L sub m, which is different from LK. And we want to show that at some moment.
And m is less than k. Assume that at some moment we have lm, m is less than k, and m satisfies this property. Then surely lk is in that family, fsm, right?
Yes. No, wait, why? Because in which okay, wait. So exact. So assume
it's consistent with sm, right?
So then LK is in the family F SM. F sub SM.
I guess, right.
Because we have some sequence of words W1, WT. They are all from L sub K, and they contain S sub SM. Then LK is in that family.
All right. So this is another minimal. So then there should be some string in LK which is not in LM, I guess, because otherwise.
Because LK is not a proper subset.
Right.
Of LM.
Right.
Because LM is the minimal here, so LK cannot be a smaller thing. So it means that LK has some word W not from LM.
And so at some moment this word
some moment we will see that word and we will enumerate in this condition will break.
Yeah.
Which just Kolya, say it again from the beginning. I lost
So our algorithm is as follows. For every ln we fix some Sn such that ln is minimal language consistent with Sn.
Yeah.
Right? At any moment of our algorithm, we find all languages ln with that property that Sn is a subset of strings enumerated so far, and all of them are in ln. And
take the minimal n.
The minimum. This is the algorithm.
Yeah.
So why it is correct?
So first, if we have our real language is LK, then for starting from some moment, we have all the elements of SK already enumerated. So K is one of the candidates. The only way why it can be wrong is because at that time we believe in some smaller candidate, some candidate with smaller index.
Yeah. So we need to find out why all smaller candidates will not qualify for LM.
Yeah. So imagine that M is smaller than K and is a smaller candidate. Yeah. Maybe at some point we will get some element of LK which is not in LM. Then, of course,
then we will eliminate.
LM will not work anymore.
So then the only case which is left is when LM is the superset of LK.
LM is a superset of LK.
But then you cannot have a condition that. Okay, so basically, then imagine that at some point you output LM. It means that all the words that you have enumerated so far, they contain S sub M. So LK is also contains this subset SM.
No,
But
what is
LK is
more into LK contains subset SM at some point.
Yeah, but SM is the subset of LM such that there are no proper subsets that also contain SM of LM. But LK is a proper subset of LM.
Yeah.
So you have LM, you have SM. And there is and everything that potentially contains SM contains also something outside. Right? So,
Okay.
well, but if we output M at some point, that means that what the real language contains SM, right? So the real language LK is also like that. But then there's something here. This will be enumerated at some moment, and this LM will be deleted from the consideration.
Yeah. So it seemed that I understood this. So is it clear for everyone, or are there some questions, or maybe we should repeat this argument? It's advertised as a simple part of the proof, so let's at least understand this one. Bruno, are you okay with the proof?
Yes, yes.
No questions.
The other part is not that hard as well. So let's give it a try. Well, let's repeat this.
Миша, Георгий, не хотите что-нибудь спросить?
No, everything's all right with me.
Everything okay. Just if everything is all right, just say something, so we will know that you are happy and we can continue. Okay.
Okay, so the other direction, let's try to see. So we want to show that if F is identifiable
in the limit,
then for every language there exists a finite subset such that
it's strange that you have now section 3 and my browser doesn't show any section 3. That's okay, I see it in Zoom, but it's funny that this doesn't really.
Maybe I should make links for any section now. But you have seen section 2?
I have seen section 2. No, now I reboot it and I can see section 3.
Okay. So we have to show that if F is identifiable in the limit, then for every language there exists a finite subset such that no proper subset of L is from F, from the family. No proper subset of L that also contains
S.
That also contains S is from F. Okay, so let's try to prove it. So
maybe Kolya can prove it also if it's not difficult.
No.
Okay.
So we have a language L. So the hint is that assume that it's not true for L, right? So there exists no S finite set with that.
So we need to prove something for every language L. So let's decide that there is some L which doesn't have this property, which means that for every finite subset.
So for any finite subset S, there is some proper subset of L which is also in the family.
Yeah.
But it has something outside. So the hint is that, okay, assuming that give me an enumeration of L where all strings of L appear, but the algorithm, okay, we have also some algorithm that's supposed to be identifying all the languages from our family in the limit. So give me enumeration of L where all strings of L appear, but the algorithm infinitely many times says something different from L. And this will be a contradiction.
And I guess that you will try to do the same thing as you do with regular languages.
That's right. More or less the same thing. Well, I have to phrase it somehow a little bit more generally, but
Okay, so let's assume there is no for this L there is no S. Let's take empty S.
let's take empty S. So we have L and we have, well, S is empty. Implying this, we have that, well, basically that there is some proper subset in the family. Okay.
So let's wait. So we don't enumerate anything, and wait until this L given us an answer.
Wait, what does it mean we don't enumerate anything? Then
No, we enumerate L's head.
L head, we start enumerating all the lengths from L head, and then the algorithm.
And then we wait until the algorithm says that
This is L head.
L head.
Right. Then let's say it was step 1. This was step 1, and let's, I don't know, if we haven't enumerated all, I mean, and also let's enumerate all strings of length 1 from L, if they haven't been enumerated for some reason. Okay, what we did after step 1 is that we have enumerated all strings of length n1 from L, and we force the algorithm to say something different from L once. Then at step 2, I want you to enumerate all strings of length 2 from L, and also force the algorithm to say something different.
No, but then we consider S, which contains of all the strings which are already there.
Yeah, that have been, so this finite S here. So maybe there is some, using the property, we know that there is some proper subset of L which also contains all of this, and we start.
Yeah.
And what we are doing?
No, I guess we start to enumerate this subset.
Right.
And again, since we don't enumerate anything else, our algorithm is forced to give this L prime at some moment.
True. Okay.
But
And
there
then
are
we do the
finitely
same.
many strings of length 1. I don't understand. We just repeat them or what?
No,
No, I
if
mean-
they are already enumerated, that's perfectly okay. So then we add strings. If they are not there, we add strings of length 2 also on the next
Yeah.
step.
The person. So
The
we
goal
want
is to get all the strings from L in the limit. So in addition to we have these languages which change each other, but they are all parts of L, and also we need that the unit of them is L. Finally, we enumerate everything. So we just artificially add some strings of given finitely many strings from L at every steps in the order of increasing length, so we cover all the strings from L. This is, I think, the plan.
No, I think the proof is finished. And just the plan is to make the algorithm change its answer infinitely often.
No, but Misha asked why we should add the strings of length 1 and 2 and so on. Why do we need this? And
but
what
we
do?
don't need this.
No. My question is another.
I think we do need this because we want to also ensure that this enumeration is that we are giving also contains all strings of L, so that the contradiction won't be with the fact that this is an enumeration of all strings from L, but the algorithm
Keeps
implemented.
doing different
Yeah,
things.
sorry. Okay, you're right. Yeah, sorry.
Yeah, Misha, say again what was the question?
Look, you enumerate all strings of length 1, then length 2, and so on and so on.
In addition to some other strings, they are not only the strings which are enumerating.
In addition to what strings?
Okay, so we start with S is 0.
This step is clear.
So, but there is some language which contains the 0 set and is strictly inside L.
Yeah, I see.
And we start enumerating strings from this smaller language until our algorithm will produce the answer that you are in this language.
Okay.
And at that moment, we artificially add strings of length 1 from L. They could be there or not. It is not clear. And declare this a new set S. So we enumerate two types of things.
So when you say that you enumerate all strings of length 1, it should be
in L.
It means that you choose a new set S containing all strings of length 1.
Containing all strings of length 1 and also all strings enumerated at the moment.
And all strings enumerated so far. I see. And you choose a language L hat for this S.
That contains all these strings.
Yeah. And produce strings, enumerate strings from this L hat. Now I understand. I have had a problem with enumerating all strings of length 1, 2, and so on. It's not enumerating. You just choose different sets S in this way.
But after our algorithm gives new answer,
I see. Algorithm
artificially add some strings.
From one.
The goal is to have all the strings from L in the limit. Otherwise, we don't have a contradiction.
We cannot distinguish L hat and L, and if L hat is stabilized answer, we change our mind. I see. Okay.
Yeah.
So it seems that the only thing we exploit here that L hat is different from L. It's not necessarily a subset, right?
No, if L hat is not a subset, then enumerating this L hat, we will go out of L and everything become disaster. Because finally we need to have L.
I see. So and we use that it is a proper subset just to know that L hat is different from L. So the answer.
Yeah. So a proper subset we need that, because if our algorithm will not say this L hat, then we will continue and the algorithm will be wrong.
Mm-hmm. Now it's clear.
Right. Okay. So now we can try to give a. So there are two options that I can also. How much time do we have? I can give a new setting, or we can try to finish this with the computable version of this theorem.
No, it's as you prefer, but just you can say what is your new nice result. It's about what?
The new nice result is, let me make section 4, that I want to give a definition of generatable in a limit.
So the new result is not about this, but is something more, another setting.
Yes.
And this is a setting you invented.
No. This is all the result. It's a Kleinberg and Mulat Tankhai, like something like that. 2024.
Oh, it's not so old. But
Yeah, no, it's some
but
kind of
no,
old.
no.
And
But do you
and it
plan
was
to explain also some new result of yours or whatever?
no. My results I will not explain. Well, we have some reprint about something, but let's
Forget about this.
forget about this.
No, Kolmogorov once explained to Uspensky that the author should start with something simple which everyone understands. Then the number of people who can understand it decreases, and as a reward, at the end the author can explain something which understands only him.
Yeah.
So, but if you don't want the reward, that's even better. Okay.
Yeah. So generatable limit. So what's the difference? Okay, so again, let me try to explain what's the difference. So you have,
But just give the definition.
so the adversary selects a language again.
So again, we have a family of languages.
We have a family of infinite languages.
Yeah.
Again, adversary select a language from the family. Again, it starts enumerating all the strings from the language in some order.
Yeah.
And we only see these strings.
Yeah.
Before, our task was to identify what was the language.
Yeah.
Now our task is to indicate an infinite subset of the language. We have to indicate an infinite subset of L. So formally, our algorithm, or is the function that maps finite strings to subsets of 0, 1 star, and the condition is that star. In the condition that
Infinite subsets.
infinite subset. I will explain what it has to do with generation. And then the property is that for any language from the family and for any enumeration, there has to be exist a moment such that our algorithm correctly indicates an infinite subset of L for all m starting from some point.
But this
But these subsets may be different, or we should stabilize them.
Right. They might be different.
So it's a weaker task.
It's a weaker task.
For example, if for this subset there is only one language in our family that is bigger, then that verse we can just say this language.
Yes. I mean, for example, if the intersection of all languages in our family is infinite, then we can just give this intersection regardless of anything.
Yeah.
So Weinberg et al., so they have solved this setting like with some relationship to this generative AI LLM stuff. Because what's the philosophy behind this? Is that what's the means to indicate an infinite subset of L? Is actually to be able to generate from language. It's like generate an arbitrarily long word from the language. So you want to say, okay, I'm seeing infinitely many examples from the language, and now I can give infinitely many words from that language.
Okay. No, whether this relates to anything practical, it's quite dubious thing. But still,
Yeah.
the definition is okay.
I should have said it, but I mean, it sort of at least makes some mathematical sense also.
Yeah.
And the theorem is that any countable family is generatable in a limit.
Any countable family is generatable.
But there
Wow.
may be uncountable families as well. Probably. Yeah, of course.
Some uncountable family can also be, and there is even some characterization of it, which I'm not probably prepared well to give.
I mean, just the set of all languages is in the is generatable in the limit.
The set of all languages probably is not.
Why? Why,
Try.
Bruno? Why?
Oh, sorry. No. Yeah.
Let's try to think. Maybe it should be easy. I think the set of all infinite languages is not generatable in the limit. But let me finish the theorem. Any countable family is not. Is generatable in the limit.
Yeah. So let's look at the set of all languages. So we are enumerating just something, and
Yeah.
imagine the opponent suggests some infinite subset. Then we would take some element which we have not already enumerated and decide that we want to avoid it and add other elements. So if the adversary doesn't change anything, then it is wrong.
So how you would obtain
By the way, I realize that I don't understand the definition. So do we need to converge? Do we need this infinite subset will be the same from some point?
No, he said it.
Not necessarily. No.
Yeah, it was already asked before.
Maybe in the algorithm I will obtain this, but
But then.
But let's try. Okay, so let's assume that it doesn't have to be the same infinite subset. No.
Yeah.
So how will you obtain the contradiction? You want to show that the family of all all infinite languages, which is uncountable.
But sorry. But what do we require? That starting from some point, our algorithm indicates an infinite subset. Yeah. So the algorithm can make some errors.
Our algorithm indicates just countably many infinite subsets. And then it's obvious because we just have, for any countable family of subsets, we have another subset which doesn't have them as subsets.
No, sorry, you are explaining what? Say it again.
Okay, I can say it. So first, your question. At every step, we can say a different infinite set, but the promise is that for each language, only finitely many times this declared subset might be not a subset.
Okay.
So that's about the definition.
Yeah.
Now, the proof that the set of all languages is not generatable in the limit.
Yeah.
So let us look to all the subsets that are declared by all possible inputs. So this gives us a countable set of sets, a countable set of subsets.
Yeah. And
now Sasha says that you can intersect, or I mean like non-intersect. So you can define a language that doesn't contain an element of countably many subsets.
And they are infinite.
Yeah. So what we do, and just as standard diagonalization from creative
so none of our sets will be a subset of our finite thing.
Yeah. It's important that they are infinite, right? Because it's like, okay, for any of the subsets, I can say, okay, this is not in my set, but I can select other sets. I mean, okay, so I need an infinite set. So, I mean, let's fix a statement. So for any family of infinite sets, so for any countable family of infinite set, there exists an infinite L such that Li is not a subset of L for all I. This is the statement, right? So how we construct this L? We do this for all I. We make sure that L is infinite. We add some elements to this, but then we take some element which is not in Li, and we decide that this is which is in L sub I, and we decide that it will be not in L.
Yeah. This is clear.
That's an old recursion theory book. Start with this argument of immune sets or something. Or
Just
creative.
we can say like this: consider an oracle which makes all the sets decidable. Then and take the infinite immune set with respect to this oracle.
Yeah.
But wait, I don't understand actually this argument. Assume that Li is the set of all strings. How we ensure that Li is not a subset of L?
Well, we
just
take-
L is contains not all strings. Why?
Sorry. I see.
Oh,
It's
the
important
bigger
that
Li is,
L
the
sub
easier
A
is
are
the
all
problem.
infinite, right? Then we can always take something which is in Li, and decide that it will not be in L.
I see. We use that Li is infinite.
No, there exists an immune set. So if all Li are decidable, we take immune set, and it doesn't
So
contain
let
any
me.
of them.
I can. So it's 20 minutes. I can prove this theorem.
Every countable
Also
family.
a computable version of it, some kind of version. And I think you can give some open questions about computable versions of that theorem. But let's prove this theorem without computability.
Yeah.
So just we want to show. Okay, can I copy this test?
What did you do? What?
I want the new section. I want just to copy theorem and start proving this. So theorem, any countable f is generatable in the limit. Now let me try to give an algorithm. So we have, f is actually there is enumeration of all languages in L, right?
Yeah.
So, and then we have a finite sequence of words of length m, some length m. And we have to output some infinite subset.
Yeah.
Okay, what we do, let's restrict ourselves.
So we need to consider only languages that contain these words, I guess.
Yes, we
Why
restrict
do we
ourselves
need other
to,
languages?
but let's first of all, I will actually just, let's forget about, let's just take the first M languages. All the other languages will not be important at the moment. And then let's take let's erase those that are, let's keep only those that contain all these words. So let's also only keep consistent languages. And there will be like, I don't know, L1 prime, L2 prime, LK prime for some K that maybe let's.
So you take the same number of words and languages. It's a bit strange, but probably it's not important.
Yeah. Then I output then I consider like all intersections. I consider L1 prime, then I consider L1 prime intersection with L2 prime, and the first intersection of the first three, and so on up to K.
But only in this order. So you don't intersect.
Only in that order.
And then probably you look which of them are infinite.
yeah, like here, I mean, they all like in decreasing the smallest infinite. Output the smallest infinite.
So just the last infinite. So they at
The
some
last
point they
The last,
start to be
the last
finite.
infinite. The last
Yeah,
infinite.
it's smallest also, but it's the last one. Yeah.
That's the algorithm. Isn't the algorithm clear?
So just the words last infinite is not clear, but if I ignore it, then everything is clear and the
No,
direction is
you
proven.
just look at the sequence and
Yeah,
see which some of them they decrease. So at some point they can become finite.
Ah, the last
You are
infinite one. Ah, okay, yeah,
you
yeah,
are obliged to produce an infinite set.
yeah.
So you cannot use those which are finite.
I
But
don't
it can
understand.
also,
Sorry, I don't understand how we construct this sequence of primate L1 prime, L2 prime.
Oh, we just select those of L1, L2, Lm, which contains strings W1 and W2, Wm.
Yeah.
But M is the same.
Strangely the same, yeah.
And what should we do if no Li up to Lm contains these strings?
Then we output any infinite set.
No, it's
Uh-huh.
just
So
some
if
kind of
if
preliminary thing.
this procedure produces some infinite length, we output it. If
Yeah, I mean,
no, we out.
you can think that if like there is also a zero element in the sequence, which is the set of all strings, and then there is this thing intersection with L1 prime, but if there is no L1 prime, you just output the set of all strings.
I see.
I don't understand how we choose that M.
M
Is the number
It's
of
just
loops
exactly the
we
number
so far.
of strings that we have in our current sequence.
The number of moves.
Sorry.
but the result is a bit disappointing because the intersection can be empty in the limit. So we enumerate infinite sets, but if we keep enumerating, we lose everything.
So we can, so starting from some moment, we enumerate infinite subsets, but the intersection of the sets can be empty. That's what
Yeah,
you're
but
saying.
it's not a requirement about the intersection and the limit, but it's
Yeah, we
still.
can, but well, wait, can we at least understand that it works in that sense?
Yeah, I agree. I agree with the proof, but I just tell that I'm a bit
you see how to
disappointed.
finish this thing. Then
Well, it's
explain.
already finished. So
No,
at
then
some point
explain
it's
why
stable.
it works. Why it will work starting from some moment.
So let's start. So let's assume that the real language that we are in is L sub k, right?
Yeah.
As before, this is the real language. So first of all, we have to wait for to obtain at least k different elements, so that our consideration will include Lk.
And this language will be always consistent.
Yeah.
Because we enumerate only things from this language. Yeah.
Then what?
So imagine that our intersection contains a string that's not in our language. How do we call it? LM?
Lk.
LK, okay.
LK is the correct language.
Yeah. And so each language that contains a string not in LK, we will drop.
Yeah, and then eventually we'll just have actually up to LK, there will be just a sequence of
languages will be bigger than LK, because
and at some
if they
point,
are not, they will be at some point they will be discredited.
Yeah. At some point, languages L1 till LK minus 1 will be dropped unless they're a subset of LK, but then we don't care about it because we only need infinite subset.
Superset of LK, yeah.
Yeah, we will be only left the supersets of LK.
Before
So the
LK, there are
all
maybe some
languages up to
supersets of
LK
LK.
will
No,
be
no,
just
but
equal to-
there can be subset of LK before, for example, L1 can be subset of LK.
No, but if it
Maybe
is
L1 till
subset, then at some
LK
moment-
minus 1 are all subsets of LK, but it's no problem. Imagine
is.
all L1, L2, all of them are subset of LK. So we will never eliminate them. But in
Supersets.
subsets.
Why
No,
not?
subset will
No.
be eliminated because we will
If
see
there are
some language in
subsets,
LK.
they will be eliminated because some element will appear which is not in them.
So it will be inconsistent with
If it's a strict subset, it will become inconsistent starting from some moment. What will not become inconsistent?
Sorry,
if it's
superset.
supersets.
Sorry, my mistake. Okay, of course. Yeah, if they're superset, but
So we can think that starting from some moment, we L1, L2, LK-1 are all supersets. It means that intersection of this prefix will be just LK. And this will be infinite. And it means that at worst we output like a larger intersection, which is also infinite. But then it will be a subset of LK at least. Right?
Yeah. It seems that.
And we make sure that we output something which is infinite. And then at the moment where already LK is under consideration, where the sequence is of strings is long enough, and at the moment where all things that are not just supersets of LK are eliminated, there will be some prefix which will be just equal to LK infinite. And then we will output some maybe larger prefix will be an infinite subset of LK because it will be a subset of LK. So that's the argument. So let me give what else we can say about that. There is a computable version which is not obvious how to which is actually not that trivial how to obtain. So a computable version, well, what you want this has to be so you have to identify this infinite subset in a computable manner, in the sense that, well, you can imagine that given, so you have a Turing machine that your algorithm has to be a Turing machine that receives a sequence of words and starts enumerating some words. And this set, and then the
so we still get the words W1, W2, and so on.
Yeah, before with that we just said, okay, there is some function that maps
No, this
finite
is
sequences of
easy to
strings to infinite
understand.
subsets.
Easy to understand in which sense we receive the strings. What is not obvious, in which way we specify the language with an infinite subset.
Yeah. So
But
we specify
it was
we just
clear.
have a Turing machine that starts enumerating the language. I mean the words.
Wait. Can I say what I understood? So there is
Yeah.
a Turing machine and it receives a list of words and then a stop symbol. And then the machine should print an infinite amount of strings.
Yes.
Yeah.
Yeah. So the last
instead of
word
producing,
is stop.
we can say that they produce a language equivalently. We can say that they produce a language by producing the enumerating machine.
Yes. And then the condition should be that for any language and for any enumeration of it, there should be a point starting from which this Turing machine, when you run this on this seed, on this long enough prefix of this enumeration, it will print infinitely many elements that are all in this language.
Okay. So
And
what is the theorem then? What is the
theorem is
effective
that
theorem?
this is possible as long as membership query for your family is decidable. In a sense, what is the membership query? So there is some enumeration of languages from the family, and it is decidable whether given x and a natural number m, whether x is from L to M.
So the sets are uniformly decidable. That's what you say.
Yes.
And so it's if and only if, or on
No,
one
just
direction.
if, just one direction.
Yeah, so if it's decidable, then it's in the limit and the proof is the same, as I
No,
understand.
it's not the same because the problem is that you don't, this proof, you have to,
We don't know which of the intersections are infinite.
Yeah.
but still you can give an alternative proof. Well, maybe somebody already sees how to do that.
Say it again. And now the Turing machine don't need to output several candidates. It just output one.
No. At every step M, we produce a candidate, and the
But
candidate is
what
a
is a
Turing.
candidate?
Candidate is a Turing machine that enumerates an infinite set.
And candidate can change.
Yeah, when we get a new WM plus 1, we get a new machine.
And a candidate is good if it is an infinite subset.
Yeah.
Okay.
Yeah. Actually, like the Turing machine can actually, it's not required that this machine on any input outputs an infinitely many strings. So actually, I mean, maybe in some small prefixes, it actually, I mean, it can output, it's in beginning and output something which is not a subset or something which is not infinite, because it will like never produce the next element. But the statement is that starting from some moment, it will produce infinitely many, given a prefix of sufficiently large length, will produce infinitely many elements
The
from
resulting machine will enumerate an infinite set, and the set will be a subset of our language.
Yeah. And the open problem, I guess, I mean, it's for me just, I guess nobody else is interested in it. Is imagine that your family is just uniformly enumerable.
Enumerable, not decidable, but enumerable.
Then is it true or not that you can also compute it? I mean, so generate computably from it.
Yeah. But then I guess people who study recursion theory should easily solve this problem. They always do something like this.
Well, I don't know. I'm also a person who have studied some kind of recursion theory,
No,
but so
you
far.
do you know how the infinite injury priority method works and what the Bushy forcing is?
Yeah, okay. So that it's some kind of argument by
No. I just
listing.
no. I just try to explain why we all are
scary word.
miserable compared to people who do recursion theory. We don't know what is infinite.
But who are these
Probably
people?
we won't need Bushy forcing.
For this theorem,
Yeah,
for open
No.
problem, we don't need Bushy forcing. I don't know.
probably not.
But we still don't know how you deal with who finished the proof, how you deal with finding the infinite intersection. So
But
for which
we are
to
out of
prime.
time. So I don't know what we should do. Is there any interest to that? There is also a computable version of the initial theorem that we can discuss. Should we?
But by the way, how much time we need to finish this proof of computable version?
Well, I can try to give it. I mean, do you want to hear it now?
No, is it
Not
5
now, I
or
guess.
30 minutes?
I mean, I can try. Let me try to tell it in 5 minutes, and when 5 minutes are gone, then we will see that.
That becomes 30. Okay.
Okay.
Okay, let's try it in 5 minutes.
Let's try in 5 minutes. Let's try in 5 minutes.
No, it just means speaker gets 10 minutes, but he tries 5 minutes.
Yeah, okay. So what I need actually is that the set of pairs.
Uniformly decidable, yeah.
Yeah, but for the argument, I will need that the set of pairs like that is enumerable. So I can eventually list all pairs of languages such that one is not the subset of the other.
Because this is a counterexample to this is finite. So
Yes.
we will.
So
Yeah.
So what's the algorithm then? I get a sequence of words of length m,
Yeah.
and then again I restrict myself just to the first m languages.
Yeah. And due to decidability, you can check which of them are consistent with this.
Yes, and then I also restrict. I can computably check which indices of them are consistent. So this is
Yeah.
consistent. Okay, and then in parallel, for all S, now I'm trying to enumerate some subset. In parallel for all S, from 1, 2, 3, and so on, I'm doing the following. So for each S, I will do the following. For some S's, this will not lead to anything actually, but for infinitely, starting from some moment, it will give me something. So what I'm doing for a given S, I am doing do S steps of enumeration of these pairs, which are not subsets, I mean, of all the pairs of our languages from our family, where one is not the subset of the other.
Yeah.
Okay, and let's think that this is kind of approximation. So
Sorry, languages are decidable or what?
Decidable.
Yeah, they're
uniformly decidable. So the fact that Li is not a part of Lj can be checked by presenting some element which is Li but not an Lj, and we can find them if it exists. So we can enumerate all these pairs.
Right. And okay.
Okay, but what?
Then take the largest I at most k, such that L1 prime, such that this Li is the subset of all previous ones.
At least is assumed to be a subset of previous one.
According to our current knowledge.
Yeah.
And
if it is not subset of
If
any,
if there is no I with this property,
yes,
then do some. I mean, then
just it's we are not produce any stupid answer because we are not ready.
yeah. No, but I mean, formally, I guess you can say that at least L1 prime will be always. I mean,
No, but maybe none of them are consistent, so we don't.
okay, you can also put, as in the previous algorithm, you can put in the beginning of your. You can actually think that your family starts. You can always add like 0, 1
Yeah.
in the beginning if you want as
Yeah.
L0 to avoid this problem. And then output some word in Li prime of length larger
No,
than
but why don't we just say that we take Li prime? Is this our answer? Why we should? We need to output some language in a form of machine that enumerates it. Why just we don't take the machine for Li prime?
Because we have this enumeration of all the pairs such that so our current understanding of all which are
You say that. Sorry. We can find that Li is no more a subset of something previous, and then this I decreases. Yeah.
Wait, we have to output some word in the intersection of all. Sorry. Not in Li prime, but in the intersection of all of them. That's important. For that, we make sure that we only can with some S, we actually will not output anything. But if we output something, first of all, let's first fix. So this is the algorithm.
Sasha, the intersection equals to Li prime, I guess.
No. This is just only our current belief.
Okay.
Yeah, actually, so what's the idea? The idea is that, so let's say my real language is that I'm enumerating from is, I don't know, LJ, right? And then I enumerating somehow from it. Then at some moment that I will have it, when I have at least J strings, I will have under consideration this language J, and I also can think that all these guys are supersets of mine, because if I take long enough, so basically I would like you to think about the moment when already there are at least J different strings, so that LJ is under consideration, and then also that all the previous languages are actually supersets
No,
of
I can say it in different way. Let's say whether it's correct or not. We start to enumerate LK prime, but also check whether they are all elements are also in the previous elements. As soon as elements fail this test, we forget about LK prime and start doing this with LK prime, LK minus 1 prime.
Right, exactly.
And as soon they are okay, we are continuing with this. As soon if we find something that's not in the previous element, since we stop, we filter it and start with the previous one.
Yeah, it's important that we do this for all in parallel. It means that, well, I mean, you have all these consistent languages, and maybe currently your hypothesis is that okay.
Yeah, we just enumerate the current thing and check that the previous one
but we
are
enumerate
okay.
everything in the intersection of all the things. If there is something, it's important because I want you to output only strings that are in this LJ.
Yeah. If it's not if an element of LK is not an element of some previous one, we forget about this LK.
Yes.
And just delete it and starting with the previous one.
Yeah, so if LK prime is not satisfy this property, actually, it will be fine in some moment, and we will...
No, we even can forget about this enumeration. It makes things easier. We just take elements and check these elements. If they are in all previous sets, that's okay. If they are not in all previous sets, we delete LK. That's what I'm suggesting.
If what element?
We enumerate LK prime. And check that all elements of LK prime are in all previous elements.
Yes.
As soon as it's not the case, we forget about LK and start enumerating LK minus 1. And since all previous elements were elements of LK minus 1, we are not in a good shape.
Yeah, that's even easier. Yeah, right. Because if we found something which is an LK prime, but not some different thing, then we can, this is not probably our language. if we have, yeah.
Yeah. So finally, we enumerate some set, which is actually a subset of all previous sets. We don't know it at any step, but at last, finally, we enumerate it.
Yes. So actually, it's even simpler, right? But yeah, I just wanted to say, right. But the argument also works if you have this thing enumerable also. But maybe the languages are not decidable themselves. But maybe this thing is enumerable.
But this is not if it's enumerable, we cannot check whether it's in previous sets or not. So at least this argument doesn't work.
Yeah, but then you need this other argument.
No, maybe you also have, but if they are not, if
Okay,
they're just
okay.
enumerable,
So there is
the pairs are not.
an argument. Your argument that works when just we assume that the membership query is decidable. So if they are uniformly decidable, then indeed your argument is simpler to understand, and it's true. Then I just wanted to maybe okay, and then we can ask if this is clear more or less.
Yes, to me it's clear and within the time limit.
No, it's 10 minutes, not 5. Yeah.
Okay. Then I would say I would just leave you an open problem and then you can solve it next time.
Okay, but if we don't do it, then you should solve it. Okay.
By the way, the recursion theory people don't have natural problems usually. So I think it's the closest to something natural.
No, they have a lot of natural problems. They're just, you are not natural enough to understand them.
Okay.
No. They definitely will say that something is very natural and it's not. For example, you can consider there is a natural problem. Can you define, maybe it's already solved, can you define 0 prime in the language of the semi-lattice ordered set of degrees? Is there some way to define it internally? No, they have many problems, but they are very complicated. Okay.
What are the ideas for the next time? Do we have any?
No, maybe you will tell us something else.
Maybe you. I mean, but you want you.
No, I can present what is called stool theorem about that a line on the projective plane has points of all complexities starting from the complexity of the line to the complexity plus n, if you want. But finally, Laurent explained me this, and it seems that I understand it. It's not completely sure, but I will check it and can.
Okay, and I learned the proof.
I can also present our preprint about that, which is actually like about. There is also some open problem about regular languages, let's say. So basically, you want to ask, okay, is for which languages you can even if the family is finite, how many? Then there is you actually need just finitely many. I mean, there is a uniform bound on the length starting from which you can. So basically, uniform generation. So I mean,
so what you say that there is some problem which you solved in your preprint, and of course we cannot understand it now, but you claim that it has some relation to this and is
the problem, for example, you have 2 regular languages. You are starting enumerating 2 two infinite regular languages.
Yeah.
If they have infinite intersection, you can just already indicate this infinite intersection. What if they have finite intersection? Then you maybe have to wait until you see all the elements in this intersection, and then you see something outside. Then okay. Then how many examples you have to see? The intersection.
Just the size of intersection.
The size of intersection. So for example, you can ask the question, if you have two infinite regular languages recognizable by n-state automata, deterministic, how large can be their intersection? Well, the intersection is recognizable by n-squared automata with n-squared state. This means that if this intersection is finite, it can have at most 2 to the n-squared words.
Yeah.
So, for example, we have constructed an example where it is like that. So the intersection is finite and has 2 to the n squared.
So what you say that what you constructed is just some example from some theory of automata.
Well, probably it's a well-known example because there is some kind of p-space bounds on something like deciding whether the intersection of finite automata is finite or something. I don't know.
No, then I guess Misha should hear this and say what is known about this in automata theory.
About what? Actually, I'm almost don't hear because the time of seminar is over and I'm doing my urgent tasks.
Вопрос такой, что есть два конечных автомата, сдающих состояниями, имеющих конечные пересечения. Какое может быть максимальное число элементов в этом пересечении?
Ну, вы, барин, задаете вопросы. Не знаю, надо подумать. Нет, я думаю, что...
Нет, вот это Саша обещает рассказать в следующий раз, а ты в следующий раз мог бы сообщить, что это известно в теории автоматов там с 1900.
Нет, ну сейчас давай я запишу тогда вопрос, потому что я боюсь, что я сейчас не в состоянии его осознать. Значит, есть два автомата, у них n состояний.
Да. Они задают регулярные множества, при этом эти множества имеют конечное пересечение.
То есть, насколько велико может быть пересечение при условии, что оно конечно?
Да.
Понятно.
А еще у нас есть теорема, что если есть два контекст-free, не существует алгоритма, который в случае, когда пересечение конечно, дают верхнюю оценку. Ну, это тоже, это все фигня простая.
Да.
Более-менее известные факты.
Да. Нет, ну просто я думал, что, может быть, вам полезно будет знать, что в теории автоматов это как-то называется, кем-то там доказано, и вот эту информацию мог бы сообщить.
Ну, я не думаю, что это прям в таком виде, прям явно... Это, грубо говоря, используется, так, я думаю, такая же конструкция, которая использует для чего-то уже использовалась давным-давно для чего-то другое.
Ну, хорошо, ладно. Ну что, тогда, значит, нет, просто если Миша в следующий раз не может, тогда нет смысла это рассказывать, потому что это важно, чтобы он был.
Я, кстати, насчет следующего раза не уверен, потому что приближается сессия, у меня запланировано прием.
Ну вот я поэтому и спрашиваю,
студента. Да. Нет, ну я надеюсь, что я успею, но как бы, так сказать, нет, ну...
Нет, давай договоримся так, что если заранее станет ясно, что ты не успеешь...
Нет, ну как это может быть заранее стать ясно? Я с ним договорился, что буду принимать коллоквиум, но это будет в 5:30. Поэтому, скорее всего, но такой студент, что он может прийти в 5:30. С ним такое бывает. Да. Там вообще странный студент. Он пропустил коллоквиум, потому что поехал домой в Белоруссию, не задумавшись о том, что в Белоруссии обучение в российских вузах не дает отсрочки от армии. И он бегал от военкомата и, конечно, не мог пересечь границу легально. Как он ее пересек в конечном счете, я не знаю, но в конце концов Белоруссия, Россия, что там, через леса. Впрочем, сейчас он уже в Москве. Вот. Но это у него заняло.
Он студент физтеха или он студент...
Нет, вышки.
Ну, тут одного уже посадили, так что пусть он будет осторожнее. Нет, ну есть такой, вот там посадили, есть такой КАЦ, с матфака его не пустили за границу и обвиняют в госизмене. Так что...
Что-то я такое слышал.
Да, но правда он пересекал границу, я думаю, в другую сторону.
Ну, во-первых, в другую сторону и вряд ли в Белоруссию.
Нет, ну, да. Нет, ну, мало ли.
Ну, и проблемы немножко другие. Нет, я думаю, что здесь вряд ли человек пострадает, но он обгомот жуткий. То есть, в общем, я скорее всего смогу.
Нет, человек, который способен пересечь границу, мне кажется, уже заслуживает уважения.
Нет, я, в общем, отнесся с сочувствием к его проблемам.
Нет, я не знаю, там проверяют ли там какие-то автобусы или как это все устроено, но...
Да я думаю, что он пешком просто прошел по лесу километров 10 и сел уже на русский автобус без всяких погранцов. Вряд ли там граница охраняется, как в советские времена, там с пограничником Карацупой и собачкой. Вот. Места просто надо знать, где там никто не шарится. Ну, а может быть, он на самом деле с военкоматом как-то решил проблему. Тут есть же и другие способы. Ну, в общем, это я у него не выяснил.
Ну ладно, в общем, тогда будем надеяться.
Давайте считать, что я, скорее всего, смогу, в крайнем случае.
Да, ну нет так нет, то значит мы тогда...
Нет, в крайнем случае я буду с Покровки, где плохой интернет, но что-то я услышу.
Да. Вот, ладно.
Ладно, до свидания.